Hello students, in the last class we have studied direction cosines of a line, direction ratios of a line. We have also obtained a useful relation between direction cosines and direction ratios also, and also we have solved some examples on finding the direction cosines and direction ratios of a line. Now in this class we are going to study mainly projection on a straight line. In that we are going to study projection of a point on a line, then projection of a segment on another line, then we are going to obtain a relation for that, then we are going to find out the direction cosines of the join of 2 points, and finally we are going to solve some examples on it also. So let us begin with the definition of projection of a point on a line. So definition is, suppose we have a point and that point is A. Okay, then if we have to find out the projection of point A on a straight line B, then for that purpose we draw a perpendicular from point A on the straight line BC. Then whatever is the foot of the perpendicular, that foot of the perpendicular is called the orthogonal projection of point A on the line BC, or simply it is also called as the projection of point A on the line BC. So the orthogonal projection hereafter we are going to call simply as the projection. Okay, so how we are defined? The foot of the perpendicular, capital P. Suppose foot of the perpendicular is capital P. The foot of the perpendicular, capital P, from a given point A on a given straight line BC is called, what it is called? It is called the orthogonal projection. Is called the orthogonal projection. And as told just now, it is also simply called as, or simply, projection. Projection of point A. Projection of point A on the line BC. So like such we have defined the projection of a point on a line. Okay, so we'll show this one diagrammatically also. So let us move to the diagram of this. So see here, diagrammatically we'll study how that projection of a point on a line is. Suppose we have a point A and we have to find out the projection of point A on the line BC. Then from that point A we draw a perpendicular on the line BC. Suppose that perpendicular is the AP, and suppose P is the foot of the perpendicular drawn from the point A on the line BC. Then as per our definition, P is called the projection of point A on the line BC, and projection is also known as the orthogonal projection. Okay, so like such we have defined the projection of a point on a line. Next one, now this projection is the same point. Okay, this projection, if projection of point A on the line BC is the point P, then this projection is the same point where the plane through the given point and perpendicular to the given line meets the line. Okay, so what does it mean? So I will show this by means of a diagram. Now observe in this figure, suppose P is a point in the space, that is in the 3 dimensions, and if we have to find out the projection of point P on x-axis, y-axis and z-axis, then how it can be obtained? So if we have to find out the projection of point P on the x-axis, then through the point P we draw a plane which is perpendicular to the x-axis. If we want to find out the projection of point P on the x-axis, then through the point P we draw a plane which is perpendicular to the x-axis, and the point at which this plane intersects the x-axis is suppose point A. Then as per our definition, A is the orthogonal projection of point P on x-axis, and this plane I have shown by the blue color. Now Similarly, suppose we have to find out the projection of point P on the y-axis. Then through the point P, we draw a plane which is perpendicular to the y-axis. That plane is shown by the yellow colored lines. So then we observe that this plane intersects y-axis at the point B. Therefore, projection of point P on the y-axis is the point B. Similarly, if we want to find out the projection of point P on the z-axis, then through the point P we draw a plane which intersects the z-axis at suppose point C. Then, as per our definition, projection of point P on z-axis is the point C. Like such, we have the projection of point P on x-axis as the point A, on y-axis as the point B, and on z-axis as the point C. So here, how we have defined the projection? So if we have to find out the projection of a point on a line, then for that purpose, we have to draw a plane passing through that point and perpendicular to the on which the projection is required. The point of intersection is called as the projection of the point on the line. So this we have shown by using the diagram also. Now let us proceed. Now next article is the projection of a segment of a line on another line. In this article we are going to study definition as well as one result about the projection of a line segment on another line. So first of all we will define the projection of a segment AB of a line on any line CD is the segment A'(B' of CD, where A'(B' are projections of A and B respectively on the line CD. See here how we are defining the projection of a line segment on the another line. So for finding the projection of a segment on another line, we have to find out the projection of end points of that segment, that is of points A and B. Suppose the projection of point A is A' and if the projection of B is B'. If the projection of point A is A' and projection of B is B', both on the obviously line CD, then we can say that A'(B' is the projection of AB on the line CD. Next, now A'(B' is the intercept made on the line CD by planes through AB, each perpendicular to CD. What does this mean? By the explanation which we have seen just by using the figure, it is clear that if we have to find out the projection of line AB on the line CD, then first of all we will find out the projection of points A and B on the line CD, and then we will get the projection of segment AB. For that purpose, we have to draw perpendicular plane from point A on the line CD, and similarly we have to draw a perpendicular plane from point B on the line CD. Then the intercept made by these perpendicular planes on the CD will be the projection of segment AB on the line CD. Now the simple example is the coordinates of a point P are suppose x, y, z. Then what are the projections of OP on the coordinate axis? See here, if P is a point having the coordinates x, y and z, then the projections are asked. So projection of point P on the x-axis will be obviously x, on y-axis it will be y, and on z-axis it will be z. So we'll move to the theorem proving an important result about the projection of a segment on another line. So the theorem is the projection of a given segment AB of a line on any line CD is AB cos theta, where theta is the angle between AB and CD. What we have to show? We have to show that the projection of segment AB on the line CD is equal to the AB into cos theta, where theta is the angle between lines AB and CD. This we have to prove. So we'll prove this. So for proving this result, first of all we'll draw a diagram, and the diagram is as such. So this is the line CD on which the projection of segment AB. This is segment AB. And we have to find out the projection of segment AB on the line CD. Then for that purpose, we draw a perpendicular plane passing through the point A, which is perpendicular to the line CD. Through the point A, we draw a plane which is perpendicular to the line CD. And suppose that perpendicular plane intersects line CD at point A'. Similarly, through the point B, we draw a plane which is perpendicular to the line CD. And suppose that plane intersects line CD at point B'. Then A' will be the projection of point A and B' will be the projection of point B. Then by definition of projection of segment on another line, clearly A', okay, the segment A', will be the projection of segment AB on the line CD. Therefore, here in this theorem, we have to obtain the length of A', B'. Our target is to obtain the length of A', B', which is actually the projection of segment AB on the line CD. So for that purpose, we draw a line which is parallel to the line CD. Okay, we draw a line. Suppose that line is AP, which passes through the point A and is parallel to the line CD, and that line is suppose AP. It is given that the angle between lines AB and CD is theta. Then clearly the angle between line AB and AP will be same as that of the angle between lines AB and CD, and therefore as the angle is given as the theta, therefore here we have this angle between AB and AP as the theta. So this is the angle of measurement theta. Okay, so this is given to us that this angle is of measurement theta. This is given to us already in the statement of the theorem. Next, now again this line, which one? This line AP is perpendicular to this plane. Line AP is perpendicular to this plane, and we know that a line perpendicular to a plane is perpendicular to each and every line lying in that plane. So as the line AP is perpendicular to this plane, therefore clearly line AP is perpendicular to line BP. This diagram is in the 3-dimensional. So this is a right angle here. Okay. So here we have lines AP and PB are perpendicular. So which means that this is a right angle. This is right angle here. So like such is the construction. Okay. Now let us move to prove the theorem. So for that purpose, as told just now, let the planes through the points A and B perpendicular to the line CD meet the line CD in points A' and B' respectively, as I have explained just now. Okay. Then A', B' is the projection of AB. We have to obviously find out A', B'. Next, through the point A, draw a line AP parallel to the line CD. Through the point A, we have drawn a line AP parallel to the line CD, and such that it meets the plane through the point B. Okay, this line AP meets this plane which passes through the point B perpendicular to CD at the point P. Okay, then obviously the line AP is parallel to CD, and therefore the angle PAB will be equal to theta, as it is given that the angle between lines AB and CD is equal to theta, and CD is parallel to the line AP. Therefore the angle between AB and AP will be equal to theta. It is equal to theta. Next one. Also line BP. Which one? This line BP. Line BP lies in this plane, and line AP is perpendicular to the plane. Therefore line AP is perpendicular to line BP. Okay. Therefore line BP and line AP are perpendicular to each other, as it is shown here by the right angle. So therefore what we have? Therefore we have this angle APB. Angle APB is equal to 90 degree. It is of 90 degree. Now then we can use the cosine of this theta. Okay, and therefore we will get, we have from this right angle triangle cos theta equal to AP. It will be equal to AP upon AB. AP upon AB. Okay. By the formula of cosine ratio, we have in the right angle triangle APB. In the right angle triangle APB, we have cos of theta is equal to the AP. AP means base upon AB means hypotenuse. This is the formula for cos theta. And from here, if we transfer this AB to the other side, then we'll get, this implies that AP is equal to the AB into cos theta. AP is equal to AP into cos theta. Now, next one. So we have obtained the AP, distance AP. Again, if you observe in this figure, then this one we have a rectangle. Which one is a rectangle? A, P, B dash, A dash. This is a rectangle. As this is a rectangle, we know that in a rectangle, opposite sides are of equal length. Therefore, AP is equal to the A dash B dash, and A dash B dash is the required projection. So therefore, we have AP is equal to A dash B dash, and hence we have A dash B dash is equal to, by using this equation, we have A dash B dash equal to the AB into cos theta. So this is the required projection of the segment AP on the line CD. So the formula for finding the projection of a segment AB on the line CD is equal to the AB into cos theta, where theta is the angle between lines AB and CD. Like such, this important theorem we have proved here. Now there is an important corollary on this theorem that will state and prove, and the corollary is direction cosines of the join of 2 points. And statement is to find the direction cosines of the line joining the 2 points P x1 y1 z1 and Q x2 y2 z2. So in this corollary, it is given that PQ is a line segment where P is the point having coordinates x1 y1 z1 and Q is a point having coordinates x2 y2 z2. Then we have to find the direction cosines of the line joining the points P and Q. So we'll prove this one, and for that purpose we require a diagram. So first of all, I will draw a diagram and then we'll prove this one. So I have drawn a diagram here. This is x-axis, y-axis, z-axis. Intersection of all three axes is the origin O. Let P and Q be the points in the space where P is x1, y1, z1 and Q is x2, y2, z2. Then we have asked the direction cosines of the segment PQ. And to obtain the direction cosines of a line, first of all, we'll obtain the direction ratios. And for that purpose, we'll proceed as it is mentioned here. So let L, M be the feet of the perpendiculars drawn from points P and Q to the x-axis respectively. So first of all, we'll find out the projections of segment PQ on the x-axis. For that purpose, we have drawn a perpendicular from point P on the x-axis, and suppose the foot of the perpendicular is L. Similarly, from the point Q, we have drawn a perpendicular on y-axis with the foot of the perpendicular at point M. Then definitely LM will be the projection of segment PQ on x-axis. Okay, LM will be the projection of segment PQ on x-axis. Next, now as the point P has x coordinate x1, therefore distance OL is equal to x1, and similarly point Q has x coordinate x2, which means that the distance OM it is equal to x2. Distance OL is equal to x1 and distance OM is equal to x2. And as seen just now, the projection of segment PQ on the x-axis is segment LM. So we'll find out LM. So projection of PQ on x-axis is equal to LM, and distance LM is nothing but it is equal to the distance OM minus OL. OM minus OL, which is equal to, but OM was x2 and OL was x1, so which is equal to x2 minus x1. Now let L, M, N be the direction cosines of the segment PQ. Then the projection of PQ on the x-axis is equal to the direction x, the first direction cosine, that is L, into length PQ. This formula we have already obtained and used right from the beginning of this chapter. So let L, M, N be the direction cosines of the segment PQ. Then the projection of PQ on x-axis is given by the formula that projection is equal to L into PQ. So which implies that, but the projection on x-axis is nothing but x2 minus x1. So equate these two things. Both are left hand side is same. So equate the right hand side. So this gives us L into PQ is equal to x2 minus x1. L into PQ is equal to x2 minus x1. Similarly, now this is for the x-axis. We have obtained this relation for the x-axis. Now this relation can be simplified and it can be written in the form. So from this we can write an equivalent form. Okay, L, what we obtained? We have obtained L into PQ is equal to x2 minus x1, and this relationship implies that this relationship implies that, means it can be written in the form. So from here we have PQ is equal to, PQ will be equal to x2 minus x1, x2 minus x1 upon L. Let us denote this relationship. First of all, let us denote this first relationship. Which one? x2 minus x1 by the relation number 1. If we denote this by the relation number 1. Okay. Now let us denote this relationship by the relation number 2. So similarly, projecting the segment PQ on y-axis and z-axis, we will get, so for the y-axis we will get M into PQ is equal to y2 minus y1. M into PQ equal to y2 minus y1, and from that we can write equivalently as this PQ is equal to, so this implies that PQ is equal to y2 minus y1, y2 minus y1 divided by M. Let us denote this by the next relationship, relation number 3. And lastly, if we project segment PQ on the z-axis, then we will obtain N into PQ. Then in that case we will obtain N into PQ is equal to Z2 minus Z1, and again this will imply that. So from this we will get, so this implies that again PQ is equal to, it is equal to Z2 minus Z1, Z2 minus Z1 upon N. Let us denote this by the relation number 4. So we have relations 2, 3, 4. Now from relations 2, 3, 4 we will get, okay. So therefore from 2, 3 and 4, therefore from 2, 3 and 4, from these three equations we get, what we get? We get x2 minus x1 by L equal to y2 minus y1 by M equal to z2 minus z1 by N, and which is equal to PQ. This relationship we have obtained. Okay. So therefore so L, M, N were the direction cosines of the line PQ. Okay. So therefore these are proportional to these one numbers, x2 minus x1, y2 minus y1 and z2 minus z1. This we obtained here. Okay. So from here we conclude that here it is divided by division symbol. Okay, at both places. So therefore from this we conclude that the direction cosines of the line joining given 2 points x1, y1, z1 and x2, y2, z2 are proportional to, they are proportional to x2 minus x1, y2 minus y1, z2 minus z1. Okay, so direction cosines are proportional to this, which means that these are actually the direction ratios. That is direction ratios. Okay, direction ratios are, which are the direction ratios? So direction ratios are x2 minus x1, y2 minus y1, z2 minus z1. So these are the direction ratios. And as we know, once the direction ratios are obtained, then the direction cosines can be very easily obtained. So like such, we have proved this corollary also. Now next article is about the projection of a broken line. See here, suppose P1, P2, P3 and continued up to the Pn are any number of points in the space, then the sum of the projections of line segments P1, P2, P2, P3 and continued up to the Pn minus 1, Pn on any line is equal to the projection of P1, Pn on the same line. So let Q1, Q2, Q3, this will prove, this result we are going to prove. Let Q1, Q2, Q3 up to Qn be the projection of points P1, P2, P3 up to Pn on the given line. Then obviously Q1, Q2 will be the projection of P1, P2. Q2, Q3 will be equal to the projection of segment P2, P3 and continued. So therefore Q1, Qn will be the projection of segment P1, Pn. Now as Q1, Q2, Q3 up to Qn lie on the same line, because we are finding the projection on the same line. Okay, so therefore for all the relative positions of these points on the line, the relation, we got the relation Q1, Q2 plus Q2, Q3 plus so on up to the plus Qn minus 1 Qn is equal to the Q1, Qn, and hence this was the projection of P1, Pn on the given line. Okay, so what does this means? I will draw a diagram for understanding purpose. Observe in the figure. See here, suppose we have a line L and P1, P2, P3 continued up to Pn are some points in the space. Then if we want to find the sum of the projection of segments P1 to P2, P2 to P3, P3 to P4 and continued up to the Pn, then the sum of these projections is same as the projection of P1, Pn on the line L. Okay, see here, for that purpose let us suppose that the projection of P1 on the line L is Q1, projection of P2 on line L is suppose Q2, projection of P3 on line L is suppose Q3 and continued up to suppose projection of Pn on line L is Qn. If it is so, then the projection of P1, P2 will be the segment Q1, Q2. Projection of P2, P3 will be the segment Q2, Q3 and continued projection of Pn minus 1 to Pn will be same as the Qn minus 1 to Qn segment. Then the sum of all these projections, okay, then the sum of all these projections is nothing but it is equal to the projection of P1 to Pn, this one. Okay, sum of all these projections is equal to the projection of P1 to Pn, and which is nothing but projection of P1 to Pn is the line segment, which side line segment, so it is the Q1 to Qn line segment. So like such we have this result. Now next article is the projection of the join of two points on a line, and the question is to show that the projection of the line joining points P x1 y1 z1 Q x2 y2 z2 on a line with direction cosines L, M, N is, it is x2 minus x1 into L plus y2 minus y1 into M plus z2 minus z1 into N. So this is the result that we wish to obtain. So let us prove this one. So for that purpose, consider that through the points P and Q, we draw planes parallel to the coordinate planes to form a rectangular parallelepiped whose one diagonal is PQ. So this diagram we have already drawn earlier. So let us go to that diagram. Observe here, we have to find out the projection of PQ. So for that purpose, we have drawn a perpendicular from point P on the x-axis and from point Q on the x-axis. Okay, then the projection will be that corresponding line segment on the x-axis. Then what we have? We have the distance PA is equal to x2 minus x1. Distance AN is equal to y2 minus y1. And distance NQ is equal to z2 minus z1. Means the distance PA is nothing but it is the difference of x coordinates of points Q and P. Similarly, distance AN and NQ are the differences of y and z coordinates of points Q and P respectively. Next, the lines PA, AN and NQ are respectively parallel to x-axis, y-axis, z-axis. PA is parallel to x-axis, AN is parallel to y-axis and NQ is parallel to z-axis. Therefore, their respective projections on the line with direction cosines L, M, N are, means then the projection of PA on a line with direction cosines L, M, N and similarly will be x2 minus x1 into L. Similarly, the projection of AN on a line with direction cosines L, M, N will be y2 minus y1 into M, and finally the projection of NQ on a line with direction cosines L, M, N will be z2 minus z1 into N. Next, as the projection of segment PQ on any line is equal to the sum of the projections of that PA, AN and NQ, means sum of the projections on these three lines, x-axis, y-axis, z-axis, okay, on that particular line. Therefore, the required projection will be equal to, required projection will be equal to x2 minus x1 into L plus y2 minus y1 into M plus z2 minus z1 into N. So this is the required projection. So likewise, we have obtained a formula for finding the projection of the join of 2 points on a line. So we have proved some results in the today's class. So we'll stop here, and in the next class we'll continue with angle between two lines. Thank you.